Okay, so let's look at the phase diagram of the iron carbon system. So from this phase diagram, can you point out what is the eutectoid and the eutectic reactions? Oh, it's already shows here. So the eutectoid reaction will occur at a composition of 0.76% of carbon content, right? Because this reaction is that one single solid transfers into two solid phase, right? Alpha and the cementite. Cementite is the intermetallic compound, right? Okay, so which composition represent the reaction of eutectic? So can you point out from this phase diagram? What's the composition? So what's the eutectic? What's this eutectic reaction? From liquid phase transfer into what? Two solid phase, right? In this case, the two solid phase, one is gamma phase, it's austenite, and the cementite, right? Cementite. Okay, so where is this reaction in this phase diagram? It's right here, right? Okay, it's right here. Therefore, this reaction is eutectic here. Eutectic here. Okay. So this reaction is that the one liquid phase transfer into two solid phase. Okay, two solid phase. Alpha and the cementite. Okay. Okay, so this is the SEN image of the ferrite. That's mean the alpha ferrite and the austenite. Okay, austenite. Okay, so the eutectoid reaction. So what's the eutectoid reaction in this carbon and iron carbon system? So heating an alloy containing eutectoid composition of 0.77 weight% of carbon above 727 Celsius produces a structure containing only austenite grains. Okay, and when austenite cools to 727 Celsius, the eutectoid reaction begins, and two phases form. The ferrite, okay, contained about 0.22 weight% of carbon, and the cementite, 6.67 weight% of carbon. Okay, so this is the eutectoid reaction. Okay, eutectoid reaction. Okay, so the composition is about 0.7607, right? And the alloys be heated up above the 27 Celsius, for example, right here. Okay, and cooling down, right? Cooling down below 727 Celsius, and two solid phase form, alpha and the cementite. Okay, it's called the eutectoid reaction. Okay, let's look at the structure. It's called perlite. What is perlite? Perlite is a lamellar structure, consists of ferrite and cementite formed in the iron carbon system. Okay. Okay. Therefore, we call this ferrite and the cementite structure is perlite. Therefore, in this phase diagram, in this phase diagram, you can see this structure. This structure is called perlite. Okay, it's called perlite. Okay, and perlite is macro constitute and provides dispersion strengthening. Okay, therefore, perlite can be as the disperse phase for dispersion strengthening. Okay. Okay, so let's look at the microstructure. Okay, so we already knew this phase diagram of the iron carbon system, right? And we already know the reaction at 0.76 of carbon is eutectoid reaction. Okay, and on the left of this eutectoid is called the hypoeutectoid. Okay, hypoeutectoid. Okay, and a right side of the eutectoid reaction is called the hypereutectoid. Wow, it's the same as that the eutectic reaction. Okay, and what's the structure of the hypoeutectoid steel? Okay, if we look at this microscope image, we can observe that the ferrite structure, right? Remember that this is the ferrite structure right here. It's a ferrite structure. It's called the proeutectoid ferrite right here. With this called the perlite structure, which is a lamellar structure, means the layer by layer structure. Okay, and this layer is consists of what? Cementite and ferrite. Okay, and what's the structure of the hypereutectoid steel? Right? What is the structure of the hypereutectoid structure? Okay, and it shows that here's the consist of the proeutectoid cementite. Okay, therefore in this region it's the cementite. This is the cementite. Okay, and the layer structure is perlite. It's perlite. The same that the perlite consists of ferrite and the cementite. Okay, so from this microstructure, these two microstructure, okay, hypoeutectoid and the hypereutectoid. So which one has the higher mechanical strength or has the higher hardness? So which one is stronger, hyper or hypo? So you can tell what's the from this image, microscope image. You tell us what's the which one is the has the stronger. Of course, the hypereutectoid steel is stronger than hypo, right? Why? Because the structure of hypereutectoid consists of the cementite, proeutectoid cementite, and the perlite. And perlite is the function of dispersion strengthening, and the cementite is an intermetallic compound, right? Therefore, the hypereutectoid steel is stronger than hypoeutectoid steel. Okay. Okay, so I already mentioned that the hypo and hyper. Okay. Hypo and the hypo and the hyper. Okay. Hypo is right here, and the hyper is right here. Okay, and we can compare the difference of this of their microstructure. Okay. Okay. Therefore, for example, for the hypo structure, initially it liquefies, right, and cooling down to reach the two phase region, right, consisting of two solid phase, okay, alpha and gamma, austenite, ferrite and the austenite, okay, and if we keep cooling, okay, if we keep cooling, and this alpha phase will transfer to pearlite, lamella structure, okay, okay, so let's look at the hyper-eutectoid. Okay, initially it's the gamma phase, right? And we're cooling down to the two phase region that consists of the austenite and the cementite. Okay, and if we keep cooling down, okay, and the microconstitute will convert to what? Convert to alpha and the cementite, right? Alpha and the cementite. Okay, like this. So you can tell the difference between this structure and this structure, right? It's consists of the cementite and the pearlite structure, and this one consists of the pearlite and the ferrite. Of course, this one is must has the higher mechanical property, mechanical strength than that of the alpha and the pearlite structure. Okay. Okay, so controlling the eutectoid reaction, controlling the eutectoid amount, increasing the carbon content, okay, increases the cementite and the pearlite, okay, hence increasing the strength till a certain peak is reached, okay, higher carbon content, the higher amount of the cementite and the pearlite. That means this its strength will be enhanced. Okay, therefore we can look at this table, shows that the carbon content corresponding to some mechanical properties, right? For example, for this one, when this carbon content reached the 0.95%, its yield stress reached the highest, and its tensile stress reached the highest. Okay, but its elongation, that means its ductility reduced. Okay, and for the fast cooling rate, for the 0.95% of the carbon, its unit stress can reach 500 megapascal. However, for the 0.8 weight of carbon, that the unit stress can reach the 525. It's higher, slightly higher than that with 0.95 carbon content. Okay, and if we compare with the mechanical property between the slow and fast cooling rate, so what's the result? What's the differences? You'll find out the mechanical properties or the strength of fast cooling is always higher than that of the slow cooling, right? Okay, so I'll introduce I will just explain the reason why later. Okay, so controlling the eutectoid reaction that control the austenite grain size. Pearlite grains or colonies grow at grain boundary of austenite. And reducing grain size or increasing number of austenite grains can increase the pearlite colonies. More smaller pearlite grains increase strength. Okay, and The other important factor is to control the cooling rate. Control the cooling rate. Increase the cooling rate during the eutectoid reaction reduces diffusion, making fine lamella. Okay. Reduce diffusion, what can produce the finer lamella. A finer pearlite structure result in increased strength. That's the reason why in the previous table shows that for the fast cooling rate of this eutectoid reaction provide higher or stronger mechanical properties. Okay. Okay, controlling the transformation temperature is also the important factor for controlling the eutectoid reaction. Okay, the solid state eutectoid reaction is very slow, and the ethanol may cool below the eutectoid temperature before transformation begins. And lower transformation temperatures give finer, stronger structure, but require longer time. So what's this mean? What's mean the lower transformation temperature? So, do you still remember? Maybe last time we already mentioned that the undercooled temperature or the supercooled temperature, the delta T, is the driving force for phase transformation. Right? If this delta T is higher, that given the finer and stronger structure. Okay, but require longer time. Of course, you know, the higher temperature difference, right? And information for this phenomena is contained in the temperature-dependent transformation diagram. It's called the TTT diagram. I will just explain this later. Okay, and two kinds of microconstituents are formed in the transformation. Okay, pearlite above 550 Celsius and bentonite below this temperature. And bentonite is a cementite precipitate as discrete rounded particle in a ferrite matrix. Okay, we can look some microscope image for this structure. Okay. Okay, so the iron and cementite eutectoid reaction. Okay, initially we only has the austenite, right? We only has the austenite. When this temperature keep cooling and the carbon start to diffuse, okay, diffuse, and the layer structure form, or layer structure grows. Okay, and this layer structure is what? Pearlite. And pearlite consists of alpha and the cementite, right? The cementite. Okay, and for this transformation, rate increases with delta T, as I already mentioned that, right? Delta T. What is delta T? The temperature of eutectoid minus the temperature that we're gonna cool to a lower temperature. Okay. Okay, so if the if this delta T is smaller, that means the foam at, I mean, this pearlite foam at higher temperature, and this pearlite, we call it coarse pearlite, which is relative soft. Okay, and if this perlite structure from at the lower temperature and it is relative hard, brittle, and stronger, that we call it fine perlite. Okay, so what's the meaning of the perlite film at the at higher temperatures? If we look at the its face there, okay, its face there. Let's erase out of this note here. So we already know this is a perlite structure, right? This is a perlite, right? No matter which composition you're just cooling down, right? Finally, you transfer to perlite structure. Okay, and for example, if we choose the one composition and these temperatures right here, maybe it's 900, 950 Celsius, and we keep cooling down below this 723, below this eutectoid temperature. Okay, so we can think of if we have two temperature below the eutectoid temperature, one is here, one, and the other one is say here, 2. Okay, so the initial temperature that I know denote as a 0. Okay, therefore from this point 0 temperature cools to temperature 1, and the structure will be perlite structure. Okay, the same thing that we start from this 950 Celsius and cools to the point 2 temperature, and the structure is still perlite. However, the microstructure are different. If we from this 0 point cools the temperature cruise to reach the 0.1, and this is the delta T, 0, 1. Okay, and if we cool the temperature from 0 point to 0.2, 0.2. Okay, and this is the delta T, 0, 2. Right? And the delta T 02 greater than delta T 01, right? And then the fine perlite will form this is the fine perlite, fine perlite, and this is the coarse perlite. Okay, get it? The difference? And fine perlite always has the stronger mechanical property. Okay, right? So we say okay, hot for fine perlite. Okay. Okay. Okay, for phase transformation or for the eutectoid reaction, transformation rate increases with the temperature of eutectoid minus temperature that we want to cool. Okay, therefore we can plot the figure to find out the fraction formation or the fraction transformation versus time with different temperature. Okay, with different temperature. For example, we have different delta T. Okay, we already know that TE, the temperature of eutectoid, is 727 Celsius. 27 Celsius, right? Okay, if this eutectoid reaction, we just cool it, the temperature cools to three different temperatures. One is 600 and 650, and the 675, right? Therefore, for this temperature at 600, has the higher delta T, and the temperature 675 has the smaller delta T. Okay, therefore for the smaller delta T, its transformation rate is slow, right? Because it needs more time. You need more time for phase transformation. Okay, I will explain this next. I will explain this. So we already know the transformation rate is the reciprocal or the inverse of the 50% of what? Of the transformation, right? Therefore, say, okay, this point is the transformation rate. And this point is the transformation rate. And this point is the transformation rate. Right? So we can compare with the transformation rate corresponding to different delta T. Right? Okay, so let's look the generation of the isothermal transformation diagram. So we can convert this transformation rate, the figure of transformation rate, to isothermal transformation diagram, or we say it's a TTT, time temperature transformation diagram. Okay, as for example, let's consider the iron and cementite system. We already know the initial concentration is about 0.76% for eutectoid reaction, right? Eutectoid reaction. And the transformation temperature is 675. Okay, and then we can plot the figure of the transformation fraction versus time, right? And we get this figure, and we can convert this figure to TTT, temperature, time, and transformation diagram. Okay, therefore we can find the growth, the initial growth time here, and the fraction here. Right, you got the point here, and you can find the 50% of the phase transform here, 50%, and finally the 100% the transformation fraction of perlite right here. Right here. Right here. Okay. So that's only for one delta T. Okay, it's for delta T is 675. Right? And we can plot different delta T, right? Different delta T of this curve. For example, I can plot this one. I can plot this one. Right? I can plot this one. I can plot, oh, disappear. I can plot this one. Right? And I can find out its transformation rate. And also we can transfer each delta T to the TTT diagram, right? You know what I'm saying? So I can plot this point, say like this point right here. And this point maybe here. And this point maybe here. Sorry, this point should be here. Okay, therefore we can plot this different delta T with the different transformation rate. And we convert this figure can transfer this figure. We can plot this point to here, right? And this point to here, and this point here, right? And we can find out this curve, right? And then we can plot this 100% of the phase transformation, right? And we can plot this maybe right here, and plot this maybe right here, and plot this point right here, and plot this point right here, right? And we can find out this this curve, right? And then we can find the 50% of the transformation fraction, right? And we can find this point right here, and this point right here, and this point right here. And you can find out the 50% of the transformation. Okay, therefore we can figure out this called the TTT diagram from this phase transformation rate of the phase transformation diagram. Okay, so I just wanted you guys to know how to plot this TTT diagram from the phase transformation rate, or for this yeah. Okay, so let's look at the case. Let's look at the case is that eutectoid composition, the C naught equals to 0.76 weight% of carbon, and the eutectoid temperature is 727, right? And the temperature began above the this eutectoid temperature, and rapid cools to 625 and hold this temperature constant. Okay, and this is called isothermal treatment. Isothermal treatment. Okay, so initially our temperature is above 727 and rapidly cool to 625, right? Let's cool it down to 625. It's right here, 625. And this temperature is hold it. Let's hold it. Okay. Okay. And then we'll find out, oh, at a certain time, this austenite starts to convert it to perlite, or we say the perlite begins to form in austenite, right? And then the 50% of the perlite structure, the 50% of the perlite structure form. And finally, the structure converted totally to perlite structure or lamella structure. Okay. Of course, you can figure out if this temperature is 600, say 600, say here, or it's 650 here. So from the, this isothermal diagram or the TTT diagram, we can figure out what's the time for the 50 weight% of the perlite foam, right? And we can estimate this reaction, the starting and the finish time. Okay, so this reaction, eutectoid reaction, will begin at this point and end at this point, right? Okay. And look at this microstructure is with the layer structure consisting of the lamella structure with cementite and the alpha ferrite. Okay, alpha ferrite. Okay, transformations involving non-eutectoid composition. Previously, we always talk about the eutectoid reaction. That means the initial concentration is exactly at the 0.76 weight% of carbon, right? If this composition is not eutectoid, how about this figure, this TTT diagram. Say, for example, we have the composition of a 1.13 weight% of carbon right here, right? Of course, we can plot its rate of transformation versus temperature and convert this figure to the TTT diagram. Okay, so it will be like this. So you can look at the, for example, we heat up a certain temperature at A50. Okay, for example, initially A50 is right here, right here. Right, therefore, in this temperature with 1.13 composition, what's the phase of this? It's completely austenite, right? Therefore, this region is completely austenite, right? And when we're cooling down to this temperature, say 800, it's cooling down to 800. What's going to happen? The structure reach the two-phase region, right? What's the two-phase region is? It's what? Austenite and cementite, right? Austenite and cementite, right? That's mean here. Let's say 800, right? Maybe somewhere here, right? And keep cooling below 728 right here. That's cooling to this temperature. So what's going to form? What's going to form? That the alpha and plus ferrite is called perlite, right? It's called P, perlite. Right? And you get it? And between this and finally you get the perlite structure. Okay, finally you get a perlite structure. Okay, in the between might be some of two phases region still exist, like the austenite and the perlite coexisted. Okay, in between. Okay, in this region, it's cementite with austenite, right? And between this blue and red line, between them, they might consist of the austenite and perlite structure. Okay, and finally, the structure will completely become the perlite structure. Okay, I already mentioned that perlite is alpha plus cementite, right? Alpha plus cementite. Okay. Okay, so let's look at another structure. It's called the Bernite structure. Okay, Bernite is another iron cementite transformation product. Okay, so what's the temperature? What's the delta T can produce the Bernite? Okay, Bernite elongated cementite particles in alpha ferrite matrix. Okay. Okay, so that's the TTT. Let's look at the TTT diagram as that when we rapidly cool the temperature to reach certain size 600 Celsius and maintain the temperature as a constant, right? And this eutectoid reaction start at this point, and this perlite fraction, the 50% of the perlite fraction form at this point, the middle between them, right? And finally, at this point is completely perlite. right? And if this temperature cool to say this might be 480, okay, this temperature still remain a constant, okay, and the same idea is that this point is the Eutectoid reaction, right? It's the beginning of the Eutectoid reaction, and this point is the 50% fraction of Burnite, and this point is that the microstructure is completely 100% of Burnite. Okay, and there's a boundary temperature. There's a temperature between this perlite and the Burnite structure. Okay, perlite and Burnite structure depends on the delta T. Okay, depend on delta T. Okay, so if we need a Burnite structure, that means we need a higher delta T, right? For example, okay, we want to form the cementite. We want to form the cementite, and this is a delta T right here, right? This is a delta T for forming the perlite structure. If we need a Burnite structure, we need a higher delta T, right? From the TE to this point, right? This is the delta T for Burnite, right? So you can tell the difference. Okay. Okay, so another microstructure for the iron cementite system is called the spheroidite. It's a spheroid means the sphere. Okay, means the sphere. So the spheroidite is the sphere structure, circle. Okay, rounded structure. So if we can look at this microscope with the structure of cementite particle within ferrite, alpha ferrite matrix, and its formation requires diffusion. Okay, diffusion, and it heat Burnite or perlite at temperature just below the Eutectoid for long time. Okay, if we need a spheroidite structure, so how to produce this structure? Okay, how to produce the structure? You have to heat up this Burnite and perlite structure at the temperature just below the Eutectoid for a long time. Okay, so that's mean if we need a spheroidal structure, we have to heat up this for example, we have the perlite structure, and then we have to heat up the temperature to reach here, maybe here. Okay, close to Eutectoid temperature, and we have to heat up this Burnite structure to certain temperature right here, close to the Eutectoid temperature for a long time. Okay, heat up to the close to the Eutectoid temperature and for a long time, right? For a long time. Okay, to fill this spheroidite structure. Okay, so you can look at the particle of cementite, right? This particle of cementite with the alpha ferrite matrix. It's the alpha ferrite matrix. Okay. And let's look at the other structure. It's called the Martensite, which is which is a non-equilibrium transformation product. Okay, so what is Martensite? As a transformation from FCC austenite to BCC or BCT Martensite. The T is tetragonal structure. Okay, tetragonal structure. Okay, so from this TTT diagram is isothermal transformation diagram. Okay. So we already mentioned that if we heat up at a certain temperature above the TE, right, above the TE, that's the 727, and if we cool down very quickly, this process is called trench. Okay, trench, and this trench process makes this transformation that is diffusionless. That means it's time independent. Okay, it's rapidly cooling. The austenite to Martensite transformation is rapid, dimensionless, and this transformation fraction depends only on what? Only on temperature. Okay, only on temperature. Okay, there's no time for diffusion. Okay, therefore this temperature is cools very quickly. Okay, and its delta T is huge. Okay, and delta T is huge. Right, from here to here. Okay, the delta T is huge. Okay, compare with other transformation. Okay, compare with other transformation. For the Martensite transformation, the delta T is huge, and the cooling rate is rapid. Okay, it's rapid. Okay, and the fraction transformation depends only on temperature, or we can say it's depends only on delta T, and it is time independent. Okay, it's time dependent. Okay, therefore, Martensite is a phase formed by dimensionless solid-state transformation. The growth rate in Martensitic transformations is so high. Okay, it's diffusionless. That's the nucleation becomes the controlling steps. And the growth rate is so high. It's not controllable. Okay, and it results from a thermal transformation depends only on temperature, but not on time. Therefore, it is time independent, right? Right. And Martensite is steel with under 0.2% of carbon content, and trenching causes the FCC austenite transfer into the BCC. Okay, and for higher carbon content, that the FCC austenite transfers into BCT martensite. Okay, the body center tetragonal martensite. Okay, so we start. We ended the course here of this martensite structure, and the next we're gonna introduce some transformation process of martensite corresponding to its mechanical properties, and we're going to introduce the other diagrams called the CCT diagram. That's a continuous cooling transformation diagram. Okay,